Welcome to The Explainer. Okay, today we are diving into an absolute masterclass on the digital nervous system of our modern world. We're going to deconstruct exactly how these massive, vast global networks manage to actually operate, the hidden limitations they kind of sweep under the rug, and the really intense cybersecurity measures needed to keep the whole thing from literally falling apart. Look, whether you're dealing with complex industrial control operations or, high-speed railway signaling, understanding this invisible flow of data is absolutely crucial. So let's jump right in.
Now, you might be wondering, in systems where thousands of devices are talking to each other at the exact same millisecond, how can vast amounts of critical data travel simultaneously without just completely colliding? Seriously, imagine millions of cars entering a highway that has absolutely no lanes and no traffic lights, yet somehow every single one of them reaches their exact destination perfectly. Well, the answer to this deconstructed puzzle is the absolute foundation of modern communications.
So, here's our syllabus for today's journey. First, the magic of packet switching. Number 2, the efficiency of shared paths. 3, the best effort limitation. 4, real-time safety challenges. And finally, number 5, defending against cyber threats.
All right, moving to section 1, the magic of packet switching.
To really wrap our heads around this, we need to nail down the core definition right away. A packet-switched IP network is basically a methodology that doesn't just, dump a massive chunk of data onto the network all at once. No way. Instead, it literally splits your data up into microscopic little packets. And then, these packets share common transmission paths with millions of other packets from other users. It's a real game changer because it allows for highly efficient use of the physical network resources.
Let's look at how this breaks down in practice. Step 1, the data is split into small packets. It's kind of like taking a huge, complicated jigsaw puzzle, putting every single piece into its own individual envelope, and mailing them separately. Step 2, these packets travel via shared paths. And they don't all take the exact same mail truck, right? They take whatever route is the fastest at that exact millisecond. And finally, step 3, the packets are reassembled at their destination based on some very strict coding instructions. It's basically organized chaos, but it works beautifully.
Okay, on to section 2, efficiency of shared paths. This brilliantly illustrates exactly why engineers jumped on this technology in the first place. You see, older models used what's called circuit switch data, and that meant a constant, dedicated connection had to be kept open for the whole entire journey. It's literally like reserving a whole interstate highway just for one single car. Obviously, if the network got dense, nobody else could transmit. But on the flip side, packet switch data completely eliminates those bottlenecks. By sharing the bandwidth, thousands of cars can weave in and out on that same highway at the exact same time. It maximizes bandwidth and makes the whole system incredibly dynamic.
Next up is section 3, the best effort limitation.
Now, the linchpin of network engineering lies in this kind of terrifying reality. Quote, the IP network, as described in its raw state, is simply a best effort network, and there is no guarantee of the packets arriving or in which order they arrive. Just let that sink in for a second. No guarantee. You could be sending critical, life-saving operational data, and the network is essentially just shrugging its shoulders and saying, hey, I'll do my best.
In the industry, we call this being connectionless. The IP network in its raw state doesn't actually establish a dedicated confirmed link before it fires off the data. And because it absolutely cannot guarantee delivery on its own, it relies entirely on a higher level protocol, the transport layer, to manage the flow, check for missing pieces of our puzzle, and ask for them to be resent if they got lost along the way. Bottom line, if you need absolute certainty, raw IP networks are inherently flawed.
Which brings us to section 4, real-time safety challenges.
So the crucial point here is, how do we bridge the gap between a best effort network and a zero failure requirement? Picture a modern control center. You've got operators staring at screens, literally dictating the movement of massive physical assets. In these high-stakes environments, a delayed packet isn't just a minor annoyance like a buffering video. It's a massive safety hazard. If a command to stop a moving train gets dropped just because the network was only giving its best effort, the real-world consequences are absolutely catastrophic. These systems demand real-time, totally guaranteed data.
And man, this creates a massive engineering dilemma. Let's look at the two warring sides here. From a safety perspective, emergency messages absolutely must be transmitted and executed immediately. Speed is everything. But From a security perspective, well, you can't just blindly trust a random message telling a massive piece of machinery to shut down. It has to be authenticated with complex cryptographic codes to make sure it's not a cyber attack. The huge problem here is that calculating and checking those cryptographic codes eats up precious time. So you have this constant, intense tug of war between the speed you need for safety and the time you need for security authentication.
Let's look at how we try to fix this in Section 5, Defending Against Cyber Threats.
Since industrial control networks mash up physical moving parts with cyber communication protocols, they are massive targets for malicious actors. To fight back, engineers deploy what's called defense in depth. This is a heavy, multi-layered approach. We're not just throwing a single lock on the front door here. We're talking real-time cybersecurity monitoring, incredibly robust firewalls to block unauthorized access, deep data encryption so even if packets are intercepted, they're unreadable, and dynamic protections against hacking and malware. And you always have to remember, a system is literally only ever as secure as its absolute weakest line of defense.
Now, what's really interesting about this slide is the physical hardware solution, because we're not just talking about software firewalls anymore. Mission-critical access demands physical resilience. We use what are called ruggedized switches and ruggedized routers that can take a real beating, extreme environments, massive temperature spikes, intense physical vibrations. And on top of that, we use enhanced duplication, so if a router completely fails or a power supply just burns out, an exact duplicate takes over instantly. That kind of redundancy is the ultimate safety net for a connectionless system.
Which brings us to the end of our explainer and to a really fascinating final thought. If our most critical infrastructure fundamentally relies on a best effort packet switching system, and then we have to wrap that entire system in highly complex, incredibly time-consuming cybersecurity defenses, will the race between network speed and cybersecurity ever actually be won? As networks get faster, the threats just get smarter and the encryption gets heavier. It's this endless, high-stakes game of digital chess, and the board is constantly evolving. Definitely something to chew on the next time you send a tiny piece of data out into the shared paths of the network.